Good morning, students. Today we are going to discuss the concept of electrostatics. Now, first let us understand what is the meaning of the word electrostatics. Electro means charge and statics means at rest. So, first we'll understand what is the concept of charge. So, what is the formal definition of charge? It is defined as the physical property of matter that causes it to experience a force when close to other electrically charged matter. Right? Now, the inherent property of matter is mass. You can see that I'm holding an object in my hand. This object is fundamentally possessing the inherent property of mass. Because of mass, it can exert and experience the gravitational force. We know that in physics, we study about four fundamental forces. The first force is the gravitational force. This is because of the inherent property called mass. The second fundamental force is electromagnetic force. We are going to study the electrostatic component of the electromagnetic force. When the charge is in the state of rest, then it will experience and exert electrostatic force. When the charge is at rest, it will be electrostatic force. But when the charge comes to the state of motion, then the force becomes electromagnetic force. Okay. So charge can be of two types, positive and negative. So as you can see here, when we have two unlike charges, they give rise to the force of attraction. On the other hand, when we have two like charges, as you can see here, there are two positive charges, there will be a force of repulsion between them. So this electrostatic force between the charges is due to the property called charge. Now let us discuss few questions based on these properties. The first question is, what type of charges attract each other? Is it unlike charges? Or is it like charges? Or is it neutral charges? Or is it similar charges? So as you have seen earlier, the unlike charges attract each other. So the answer will be what? The unlike charges attract. Okay. Now next, let us talk about what type of charges repel each other. Is it unlike charges? Is it like charges? Is it dissimilar charges? Or both A and C? The answer is like charges repel each other. When the both charges are positive or both charges are negative, the force between them will be a electrostatic repulsive force. Now let us try to understand how do we measure the charge. So the SI unit of measurement of charge is Coulomb, and it is defined in terms of the fundamental physical quantity, that is electric current, right? So in this definition, 1 Coulomb is the amount of charge conducted by the wire in 1 second if the current flowing through it is 1 ampere, right? So we in this system, we also use a basic unit or electronic charge, that is the charge held by one electron, or a proton, that is given by 1.602 into 10 power minus 19 coulombs, and it is considered to be a universal constant. And according to quantization principle, what we can say, Q is equal to N into E, where N is the number of electrons, E is the charge held by one electron. So when we simplify this term, we get the value of N as Q divided by E. And if we consider a charge of 1 coulomb and the charge of electron as 1.602 into 10 power minus 19, we get the answer as 6.25 into 10 power 18. So 6.25 into 10 power 18 electrons constitute a charge of 1 coulomb. But practically, this large magnitude of charges are not found in the real life. In the real life, we have the charges of magnitude picocoulomb. 1 picocoulomb means 10 to the power minus 12 coulomb, or 1 nanocoulomb, that is 10 to the power minus 9 coulomb, or 1 microcoulomb, that is 10 to the power minus 6 coulomb, or 1 millicoulomb, that is 10 to the power minus 3 coulomb. So if you compare with these many number of electrons, so it is very difficult to add or remove these many number of electrons from a given body. So practically, if we remove, say, around 10 to the power 9 electrons from a body, then the charge held by the body will be approximately 1 nanocoulomb. So let us try to answer a few questions based on the fundamental properties of charge. So can you try to answer it? The law of conservation of electric charge states what? Does it state that the isolated system net charge will increase, it will decrease, it will remain constant, or it will become zero? The answer is it will remain constant. That is called the conservation of charge principle. So if there is an isolated system which holds two objects A and B, and initially A held a charge of Q1, B held a charge of Q2, and they are allowed to exchange the charges, then what will happen? After some time, A will acquire a charge of Q1 dash, B will acquire a charge of Q2 dash. Total initial charge was Q1 plus Q2. Total final charge is Q1 dash plus Q2 dash. According to the conservation of charge principle, for the isolated system, total initial charge, that is Q1 plus Q2, will be equal to total final charge, that is Q1 dash plus Q2 dash. That is known as the conservation of electric charge principle. There is another application of conservation charge principle. When we rub two objects, then what happens? The electron jump from one object to other object. So in the case of glass rod rubbed with silk, what will happen? The electrons are lost by the glass rod. When the electrons are lost, then naturally we can say that for the glass rod, number of electrons becomes less than the number of protons. So it becomes positive charged. Glass rod becomes positively charged. But at the same time, the silk which has been rubbed with it, it has gained electrons. And because it has gained electrons, so the number of electrons has become number greater than number of protons. So it will become negatively charged. Okay. So this is also the application of a conservation of charge principle. The total amount of charge remains same, but the amount of electrons which are lost by the glass are gained by the silk. So what type of charge the silk will acquire? The silk will acquire a negative charge. Reason you understand? Because the number of electrons has become greater than number of protons, so it will acquire a net negative charge. Now the material, on the basis of their electrical property, they are classified into three types. They are conductors, insulators, and semiconductors. Now, in the case of conductor, we can say that this is the material through which the charges can flow easily. Why the charges are able to flow? Because it holds free electrons. Free electrons means what? Loosely held electrons. So when the potential difference is applied, these free electrons or these loosely held electrons, they are able to flow easily, and because of that it is given a name of conductor, because it can conduct electricity, so it is called conductor. The example is most of the metals are good conductors. Now, so far as the charge bearing capacity is concerned, when the conductor gets charged, for example, if it gets positively charged, and when it will get positively charged, when the electrons are removed from it. When we remove the electrons, then it will become the positively charged, right? Now, when it becomes positively charged, and because of the mutual electrostatic repulsion, the charge will get distributed uniformly on its surface. That is the property of a conductor. When we talk about insulator, they do not have free electrons. So, because they do not have free electron, so the electricity will not flow or will flow very poorly through it. So, when we talk about the examples, silk, cotton threads, rubbers, and many plastics are good insulators. So as you can see here, whenever the charge is given to an insulator, it will remain confined only in one part or one segment of the object. So as you can see here the body is insulating body is given a positive charge, and that positive charge is held on only on one side, that is the right hand side of the object. I hope you can understand the difference between the conductor and insulator. Here, all the charges localized because there are no free electrons, so this charge cannot move at its own to the other point. So wherever we keep the charge will stay at its own location. Now, in the case of semiconductor, its properties are lying in between the conductor and insulator. So, the conductor will have few free electrons and atoms with a bound electron both, right? So, the example can be those in the germanium, silicon, gallium, arsenic. All these are the examples. When we try to study the comparison between conductors, semiconductors, and insulators, we see that the conductors have moving electrons, and basically the atoms in a conductor will have a moving electron or the free electron, but inside the insulator it will be a bound electron. So we can see that because the conductor has the atoms with free electrons. So when a potential difference is applied by using a cell of, for example, 1.5 volt, then the current flowing through it is directly proportional to the potential difference applied. That is nothing but Ohm's law, that is obeyed for conductor. In the case of insulator, we see that the atoms have bound electrons, so the value of current will be 0 in this case. In the case of semiconductor, because there are some atoms which have free electrons, actually in the case of semiconductors we use the terms holes and electrons as the charge carrier, that we'll understand in the due course of time. But primarily the difference between conductor and insulator, although the insulator is allowing the current to flow, but it does not obey Ohm's law. Does not obey Ohm's law. So the semiconductor will not obey the Ohm's law, conductor will obey the Ohm's law. I hope the difference is clear. Now we talk about electrification. When we try to impart the charges on the surface of a body, then the process is known as electrification. So there are different methods of electrification. One is charging by friction, other is charging by conduction, and next is charging by induction. When we talk about charging by friction, then two neutral bodies are rubbed together and the charge is transferred from one to other, right? So for example, if there is one insulator, as you can see here, there is a balloon which is rubbed with the wall, then what will happen? It will acquire some negative charge, right? And because of negative charge, it will cause polarization of the particles of the wall. So you can see that on this side, it has become positively charged because it is lying close to the negatively charged balloon, and the electrons, they will be repelled by these electrons, but these are not free. Wall does not have, it is not made of conductor, it is also made of insulator. So what will happen? The electrons will be repelled, so it will get polarized because of the presence of the charged balloon. Instead of insulator, if it was a conducting slab, then what will happen? All the electrons will get deposited on this side and all the positive charge will get deposited on this side. That will be called charging by induction. So charging by polarization, charging by friction is possible only for insulators, but charging by conduction and charging by induction will be possible for conductors. So we can see that charging by friction is for insulators, and charging by conduction and induction will happen for conductors. Okay, let us try to answer a few questions based on it. So when a glass rod is rubbed with silk, the glass rod loses electrons. and still gains equal amount of electron. This process is called what? Because they are brought in physical contact, so it is called charging by friction. So in the charging by friction, what is necessary? Physical contact is necessary. Similarly, when a charged object is touched to an uncharged object, again by touching, what do we mean? We mean that physical contact is there. But this process is applicable only for conductors. And because it is brought in physical contact, so this will be called charging by conduction. This method is called charging by conduction. So when one charged object is touched with another uncharged object and the uncharged object is a conductor, then because of charging by conduction, because of the physical contact, the charge will be conducted and this other body will get charged. But if a positively charged body is brought close to uncharged body, the negative charge of the uncharged body gets accumulated on the same side. This process is known as, this is called charging by induction. Here it is brought close, but there is no physical contact. If there is no physical contact, means there won't be any transfer of charge, only the induction of charge, right? So if this is a positively charged rod and this is a conductor, then it will attract the electrons here and the positive charge will get accumulated on the other side. So if this is having a plus capital Q charge, on this side there will be a minus Q charge, on this side there will be a plus Q charge. If you look at this isolated conductor, then the total initial charge was 0 because it was electrically neutral, it was uncharged, and final charge is also 0 because on one side there is a plus Q charge, other side there is a minus Q charge, total final charge is 0. So it is also based on the conservation of charge principle. So charging by friction and charging by induction both represent the conservation of charge principle. Charging by conduction, we are adding the charge so the system does not remain isolated. Now we talk about the Coulomb's law of force. The law is very similar to the Newton's law of gravitation. I hope you remember it. There it said that F is equal to capital G m1 m2 by r square. Here, if the two charges are in the state of rest q1 and q2 and they are point charges separated by distance r, then F is given by some constant. That constant can be called Coulomb constant and q1 q2 by r square. Here, epsilon naught is called permittivity of air or free space or vacuum. So epsilon naught is 1 divided by f by 4 pi. I can shift this epsilon naught here. I can shift this f here. So it will be 1 by f into 4 pi into q1 q2 by r square. So the value of epsilon naught is 8.85 into 10 to the power minus 12. When we talk about its unit, because q1 and q2 will be measured in coulomb, so the numerator will be coulomb square. Coulomb into coulomb is coulomb square. And the force will be measured in Newton. So it will be divided by Newton and r square will be nothing but meter square. So it will be coulomb square per Newton meter square. That will be the SI unit. And the value 1 by 4 pi epsilon naught is taken as 9 to 10 to the power 9 Newton meter square per coulomb square. You can see that the unit is just reverse of each other. When we talk about the Coulomb's law of force in the vector form, what do we notice? If there are two charges, Q1 is situated at a position R1, Q2 is situated at a position R2. If the coordinates of Q1 are x1, y1, then the value of R1 vector will be what? x1 I cap plus y1 j cap. And the point charge Q2 is situated at x2, y2, then its position vector will be R2, that is x2i plus y2 j cap. Then R21, that is the position vector of 2 with respect to 1, will be R2 minus R1, that is x2 minus x1 I cap plus y2 minus y1 j cap. And in terms of the vector form, the force experienced by the charge Q2 due to Q1, as you can see here, it is a repulsive force that will be kq1 q2 into r21 divided by mod of R21Q. So when we put this value of R1 and R2 here, we get this result. I hope this formula is clear to you. Now, if the two charges are kept in a medium, not in vacuum, but in some other medium, then the force in the medium will be given by 1 by 4 pi epsilon naught Q1 Q2 by R square, where epsilon is called the permittivity of the given medium. That is nothing but epsilon naught into epsilon R. Epsilon naught, you understood, it is absolute permittivity. Epsilon R is the relative permittivity of the given medium. It is also represented by capital K, that is the dielectric constant of a given medium, and on comparison the effective air distance between them will be given by R dash is equal to R into root of epsilon. If the medium is partially filling the space between the two charges, then F will be Q1 Q2 divided by 4 pi epsilon naught into R minus T plus T root K, where T is the thickness of the slab or the medium present between the two charges. R is the total distance between the two charges. For air, the value of epsilon R, that is the relative permittivity, is 1. And if we put the value of epsilon R as 1, then you can see that the value of the force will become 1 by 4 pi epsilon to Q1 Q2 by R square. That is same as the force between the two charges in vacuum. Now let us try to answer a few questions. The Coulomb's law is true only for what type of charges? Is it for moving charges, static charges, both? The answer is it is true only for static charges, because Coulomb's law is for electrostatic force. Other question is the force of attraction or repulsion between two stationary point charges is how it is related to the product of charges. Then the relation is it is directly proportional, because the law is what? F is proportional to Q1 into Q2 and F is proportional to 1 by R square. This represents the force is inversely proportional to the square of the distance between the two charges, and this part means that force is directly proportional to the product of the charges. Now, what is the condition that should be satisfied for the Coulomb's law? The answer is both A and B. It is true for static charges and it acts along the line joining the two charges considered to be the point charges. Now, let us see a very simple question. Let us assume there are two copper spheres, each of mass 1 gram. They are separated by 1 meter. We know that the atomic mass of the copper is approximately 62.5. So 1 mole of copper will hold these many number of atoms, and the charge of 1 proton is same as the charge of 1 electron in magnitude, that is 1.6 into 10 power minus 19. It has 29 protons in the nucleus, so this will be the total nuclear charge. And the question says that the charge on the sphere is 1% of the total charge, so it will be 1 by 100 times of the total charge. That value comes out to be approximately 4.298 into 10 power 2 Coulomb. By using the formula F equal to kq square by r square, we can find the force. Now let us see the Coulomb's law in the vector form. So this question says that there are 8 identical charges which are placed at vertices of a cube of side 1 meter. We have to find the force on any one charge due to the rest. So here let us assume that this charge number 1 is situated at the origin. Charge number 2 is situated at x-axis with a coordinate 1, 0, 0. Charge 3 is situated in the xy plane with the coordinate 1, 1, 0. Charge 4 is situated on the y-axis with the coordinate 0, 1, 0. Charge 5 is situated in the yz plane with the coordinate 0, 1, 1. Charge 6 is situated at this corner, that is 1, 1. Charge 7 is situated in the xz plane with the coordinate 1, 0, 1. Charge 8 is situated on the z-axis with the coordinate 0, 0, 1. So I hope you have understood the coordinate of the different charges. You can copy down this diagram. Now what is the formula for force? F21 is given by K Q1, Q2 into R21 divided by mod of R21 raised to the power 3. So if I focus on charge 6 and I try to find F61, then it will be KQ1 into Q6. That is, both are equal. And R21 in this case will be R6 minus R1. R6 will be I plus J plus K. That is 1 comma 1 comma 1 for point 0.6. And for the origin, that is R1 will be 0. That will be I plus J plus K, and its numerical value R61 will be what? Root of 1 square plus 1 square plus 1 square. That is root 3. So we can write I plus J plus K divided by root 3. That is how F61 will be calculated. For F62, we have to focus at the point 6, that is I plus J plus K, and point 2, that is 1 comma 0 comma 0, that is 1 I cap. So when we subtract, we get I plus J plus K minus I, that is J plus K, whose modulus will be root 2. In the similar manner, when we focus on F63, we talk about R6, that is I plus J plus K as usual, and point 3 will have a coordinate of I plus J, that will be only K cap, modulus will be 1, so it will be root 1 cube. When we talk about F64, then we will focus at point 6, that is I plus J plus K, and point 4 is only J cap, so it will be I plus J plus K minus J, that will be I cap plus K cap, the modulus will be root 2. Similarly, when we talk about F65, that is the point 5 here, so here it will be J plus K, that is J plus K we write here, the modulus of the R will be 1. Similarly, when we talk about F67, this is point 7, that is I plus K. So this will be the R vector and this will be the modulus. Similarly, when we talk about F68, the charges at point 6 and point 8 are to be considered. So it is I plus J plus K minus of K cap, and modulus will be root 2. When we talk about the net force experienced by the charge situated at point 6, this will be the result. Okay, thank you very much.